Hi guys. So I am going to talk about how this obstruction to lifting line bundles or deforming line bundles can be viewed as a certain cut product with Kodaira-Spencer. Okay, so here's the setup. So we're going to let R be a domain. Okay, so it's like a Noetherian ring. You can take it to be a field. Okay, and then we're going to let D1 of R be the infinitesimals of R. So this is this ring here where we join epsilon, and we say that epsilon squared is 0. Okay, and then we're going to take X a scheme over R. So X is going to be scheme over R, and we're going to take L to be a line bundle on X. So this is just going to be a sheaf. So I'm in this video I'm going to view it as a locally free sheaf. So so there's going to be a cover of X such that this guy here locally is going to be isomorphic to just the structure sheaf of X. Okay, and so the theorem says the theorem that I want to talk about in this video, and so this is like so this is like a baby cut product with Kodaira-Spencer. So it says that so if we have a deformation of X to, let's say, the dual numbers. Okay, so we have a equicharacteristic deformation, and then the following is true, that the obstruction is a certain cut product. The obstruction to lifting the line bundle is going to be a cut product with Kodaira-Spencer. So this is the Kodaira-Spencer class of the deformation, and here this is the logarithmic derivative of the class associated to L. Okay, so as we remember from the line bundle video, this inner part, okay, will be in okay, so this is an H1 of the multiplicative group, and so this one thing is going to be an H1 of X omega 1 X over R, so the differentials. Here, this thing is in H1 of the tangent bundle, here, and then here, this is the obstruction class, and this is going to live in H2 of X OX, okay? But really, here, if you remember the class from the obstruction class, this is also we've used the isomorphism that this is really H2 of X, and then we do 1 plus epsilon O of X here. So we're really viewing this as a subsheaf of the multiplicative group of X tilde. Okay, so the important formula is this, and this is what I want to show. Okay, so let me say some things that are going to come into play. Okay, so one of the things that come into play is this the exponential sequence. So so this is the formal exponential sequence here. So we have really this is the sequence, and this is what I was talking about here. 1 plus epsilon OX. So this goes into the multiplicative group of the deformation, and there's this quotient map here, and this is the kernel of the quotient map. Okay, and in this theorem we just identified with this. So these are isomorphic abelian groups here. Okay, this d log here. Okay, so that's one thing that comes into play. So this d log is so this is the map of sheaves, and this is induced on cohomology here, here to omega X over R, and so this is given by if we take some element, so we just do df over f, so it's invertible, right? So this makes sense. Okay, the other thing was this here, so this will come up again. I'm going to say this real quick, but you can see the videos on classification of line bundles if you want to see that. Okay, so in order to do this, let me say a little bit more. Okay, so Okay, so what we're going to need to do is, so here's the proof. Okay, so what we need to do is we need to fix, so let's take UI X. Oh, I need to say something else. Okay, see, these deformations need to be smooth. Okay, so, okay. So I'm going to use smoothness to get a certain map. Okay, so here we're going to have a cover. Okay, and what we're going to do is we're going to let phi I. Okay, so this is going to be a map from OUI tilde. So this here, okay, is the pullback of the deformation, okay, to UI. Okay, so this is going to be the thickening of X tilde above UI. Okay, so this is the same part of the open subset of. Okay, so another way, if you don't want to think about it this way, you can think about it as so this could be also equal to, so this is what I'm going to use by this notation. So we're going to view them as locally ringed spaces, and here we have a sheaf, and then you can just take this to mean this. So it's the sections above UI of this new deformed sheaf. Okay. So we have this nilpotent extension, so then the underlying topological spaces are the same, okay, but the structure sheafs are different. Anyway, so we need to identify this with here, O of UI epsilon. So this is the trivial deformation which exists in equicharacteristic, and this guy is just the dual numbers of O of UI. Okay, so any two deformations, this is the gerb property of deformations. Locally, any two deformations are going to be isomorphic. Okay, so we have an isomorphism like so. Okay, and recall that the Kodaira-Spencer class, okay, it looks like a bunch of derivations here. So this is in H1, and then so let's call this thing U of the relative tangent bundle. So this is just the sheaf of derivations here, and how these two things are related is the following. So it says that phi ij. Okay, so this guy goes from here. So this is equal to phi j inverse composed with phi I. Okay, and what it does to guys like this. So these guys here are elements of O of UI. And it just takes A to be the same thing, but now what it's going to do is it's going to take B plus, and then we transition by taking this derivation like so. Okay, so this is how the transition data is related to derivations. And I did a video on this in general. So I think I did it for maybe nilpotent extensions. Or if I didn't do it for nilpotent extensions, I did it for general square zero extensions, even a mixed characteristic. Okay, so we have this here, and so this defines the Kodaira-Spencer class. Okay, and so then recall that okay, so this is what we had. Okay, and then I guess we need to recall the definition of the obstruction. And then we need to recall the class for the line bundle, and I did a video on that as well. Okay, so so let's just say that, let's suppose that the class of this line bundle is equal to Fij here. Okay, and so this will be an H1 of U of O times. Okay, so so we have the Kodaira-Spencer class. We have this. This is how they are connected, and the phi i's are connected, related. Okay. What else do I need to talk about? I think we're ready to start proving the theorem now. So let's recall the definition of the obstruction. So what we can do is first let's define. So recall that the obstruction class. So what we'll do is so first define Vij tilde here in, let's say, O of x tilde Uij, or, you know, O of Uij tilde to be the element, okay, this is times, such that, okay, when we do phi of this guy, okay, we just get Fij plus epsilon times 0. Okay, so I'm just gonna like lift this in a stupid way. Okay, I'm gonna make it so that when I use my trivialization here, so I make it look locally like the stupid deformation, that it's just going to extend by 0. Okay, so using that, recall that whenever we had any special lift here, we could define the obstruction to deforming, and the obstruction to deforming the line bundle, as we recall, the obstruction to deforming the line bundle was defined to be Fij tilde, Fjk tilde, Fki tilde. Okay. Another constraint. Let's say here also we're going to have that Fij tilde inverse is F tilde Ji. Okay, so we're also going to make this choice. Okay, so this was this class here, and this was in H2 of X, and then we had 1 plus J in the video, but 1 plus epsilon OX. So in the so in the obstruction to lifting video, the obstruction deformation theory of line bundles, we had this. Okay, so now I'm going to show you how this class is going to be the cup product with the Kodaira-Spencer. Okay. Okay. So here's what we do. We just compute. Okay. So here we're just compute. So we compute. Okay. And so what we compute is we're going to compute phi of Jk, Fki here, tilde tilde. Oh, I guess here we're gonna do this. So we want this to be in, so I wanted to actually take this, Phi. Like so. Okay, so Phi goes from, where does it go from? So Phi goes from here to here. Okay, so this makes sense. So here, we want it to be in this thing here. Okay. Well, I mean, you can view this in both ways. Okay. Okay, so what I want to do now is I'm just going to compute phi of Fij tilde, Fjk tilde, Fki tilde. Okay? And so to do this, I'm going to use the formulas that we previously established. Okay, so that how these Fi tildes behave. Okay, so this is a ring homomorphism, so we can break it up like so. Like so. Okay. And then what I'm going to do is I'm going to introduce, so here I'm going to introduce things so that we get some extra transitions So here we're just going to have the same thing. So this is phi Fij tilde. Okay. Now here I'm gonna introduce phi, then I do phi j inverse phi j. Okay. So these cancel with each other and phi j k tilde. And now I can apply the definition that we had before. Okay. Now we're going to do the same thing. We have phi k. Now we're going to do. So what do we do? Sorry, this is phi I still. So this is phi I, and then we have phi k inverse phi k, f k I tilde, like so. Okay, and then here we're going to get a transition map, and here we're going to get a transition map. And then the rest of them, this is going to be Fij, okay? And so then this is Fij, and this is Fjk. And this thing here is phi ik, and then we have fki here, like so. Okay, now we apply how these behave under these transition maps in relation to the Kodaira-Spencer cocycle. So in particular, here this is 1 plus epsilon. And here we have theta ij, fjk. And then here, oh sorry, so we have fjk here to begin with. And then here we have the same thing. So we have fki plus epsilon theta ik fki. Okay, so here, we're just going to expand out. So this is Fij, Fjk, Fki. Okay, and then we have epsilon. And now we're going to collect all the pieces with epsilon. So we can have this one, and this one. So this is Fij, theta ij, Fjk, Fki, plus, and now what else can we have? We can have this one and then these two. So Fij, fjk, let's see, fjk, and then we can have theta ik, fki. Okay, this is a cocycle, so this is 1 plus epsilon. Okay, now we can already see we're in the right space. Okay, so now what do we have? So we can put these two together, and here we can do Fij, fjk, fki. So I introduced an fjk, so I need to do fjk inverse here. This becomes 1 theta ij fjk. Okay, plus, and then here fij fjk. This is fik theta ik fki, like so. Okay, so let's write this out. Let me just clean this up. Epsilon. So here we have fjk inverse theta ij fjk. Okay, here plus, and then we're going to have this thing over here, ik, and I'm going to claim that this term here is actually 0. So I claim that this is going to be 0. Actually 0. Okay, so but here, let's suppose this is 0 for the moment. If this is 0, then we can see that this thing here, so this thing looks like theta ij of fjk over fjk inverse here. And this becomes equal to, so this is equal to d log fjk. This is, here we have some type of inner product with theta ij. So there's going to be d's involved, and when you pair d's with derivations, this is the duality. And so this is a cocycle representing the cup product. The cup product that we wanted. Okay? So it remains to show that that's 0. So it remains to show fik theta ik fki is equal to 0. Okay, so now this part's going to be a little bit tricky. So let's notice the following. 1 plus epsilon fik theta ij fki. Okay, so this is really fik times, let's say, phi ij. So let's do this. This is so phi ij. So I'm going to get an extra phi ij here. Okay, so this is really, so this is this. This is fine. Phi ij, phi, let's see, phi ij. Oh, sorry, this is phi ik here. Okay, sorry. Okay, so this is phi ik here. So this is this times, let's do this, phi ik. So then we can do phi ki plus theta ik phi ki. Okay, so this is phi ik. Now we're going to do phi ik here. Then, so this is the transition of fki. So this is fik, phi ik. And then here we do phi k. And then we do fki tilde. So this is the trick. Fik, fi, fk inverse phi k, fki tilde here. So this is fik. Now we see that this thing here is, so what is this? So this is phi. This part here is, so what is this? So so this is, sorry. So this is phi, yeah. Fik tilde inverse, like that. So this is fik. And so now this is phi of f tilde ik. This is a ring homomorphism, so we get that. Fik here. And this becomes now phi ik inverse. So this part here, all in the parentheses, becomes phi ik. And this is just 1. Okay, so these cancel, okay, and then we get this is equal to 0, so this implies that epsilon fik theta ik fki is equal to 0. Okay, as advertised. Okay, and that's the proof.